Hello, everyone. Welcome to today's first session. Our first speaker is Iman Marvian from Duke University, and he will be speaking about local symmetric quantum circuits. Iman, time is yours.
Perfect. Thank you so much. Hello, everyone. My name is Iman Marvian. I'm based at Duke University, which is located in North Carolina. So current local time in North Carolina is a few minutes after midnight. And I hope I can stay focused and present a coherent talk. I will do my best. So in this talk, I present some recent results on local symmetric quantum circuits. This is an ongoing project in my group. We study quantum circuits where local gates have certain symmetry. For example, they are invariant under rotations around Z. And we study various properties of this type of quantum circuits. So in particular, in this talk, I'm going to focus on the question of universality. So a very well-known result in quantum computing states that any unitary transformation on n qubits or n qubits can be implemented by a finite sequence of two local unitaries that acts on 2 qubits or 2 qubits, and it can be implemented exactly. This result, of course, we now take it as a kind of basics of quantum computing. Everybody knows that, but it's interesting that this result was discovered only in 1995. So before that, meaning that after the discovery of Shor's factoring algorithm. So before that, people thought you need 3 local unitaries based on this result by David Deutsch in 1985. So he showed universality of 3 local unitaries. And then later in 95, David DiVincenzo and then Seth Lloyd, they showed how you can achieve universality with 2 local gates. Okay, so this result was discovered in the context of quantum computing, but in a way you can argue that this is a fundamental fact about composite quantum mechanical systems that interact by local Hamiltonians. So we know that locality puts various constraints on the time evolution of the system. For example, it implies the finite speed of propagation of information in the system, as it's highlighted by Lieb-Robinson bound, for example. So locality restricts the time evolution of the system. However, this result, this universality, implies that in spite of this constraints, the constraints that are imposed by locality, still, if you give the system enough time, after a sufficiently long time, it can experience any arbitrary unitary evolution under a local Hamiltonian. So locality doesn't restrict possible unitary evolutions that the system can experience after a sufficiently long time. So this idea of universality, together with other results in the framework of quantum circuits, like ideas about complexity, etc., they have found extensive applications in different areas of physics beyond quantum computing, from classification of phases of matter to quantifying complexity and understanding scrambling and quantum chaos. So this is a very important result beyond quantum mechanics. That's the point I'm trying to make here. Sorry, beyond quantum computing. So in this recent work, I basically revisited this classical quantum computing result, and I asked what happens when we study locality and symmetry together. In particular, does the universality of 2 local unitaries, or more generally k-local unitaries that act on k qubits or k qubits, does this universality remain valid in the presence of symmetries and conservation laws? In particular, do local symmetric unitaries generate all symmetric unitaries or not? Of course, if all of these local unitaries respect the symmetry, for example, they are all invariant under rotation around Z, the global unitary that's generated by them also respects that symmetry. So the question is, can we implement all global unitaries that respect the symmetry using local unitaries that respect that symmetry? And this question, has studying this question has implications in different areas of physics: quantum chaos, quantum control, quantum thermodynamics. Here, for this audience, I'm going to focus on an example of quantum thermodynamics. So in quantum thermodynamics, and in particular in the resource theoretic approach to quantum thermodynamics, we are interested in the notion of, fundamental notion in this framework is the notion of energy conserving unitaries. Unitaries that conserve the total Hamiltonian or total energy of a system. So in particular, in the resource theory of quantum thermodynamics, it's usually assumed that a global energy conserving unitary can be implemented with negligible thermodynamic cost, right? So here is an example. For example, I have three systems. Let's say they are spatially separated from each other. System 1, system 2, system 3. They are not interacting with each other, but I want to implement a unitary that couple them and conserve the total Hamiltonian H total, right? So now the question is, so in the resource theory of quantum thermodynamics, we usually assume that this is free in the language of resource theories, or it can be implemented with negligible cost. Now the question is how we can implement that. Like, if we are restricted to local operations that preserve energy, how we can implement a general energy conserving unitary. So in particular, can we obtain all energy conserving unitaries by combining two local energy conserving unitaries? Or perhaps there is some hidden thermodynamic cost for implementing a general energy conserving unitary if we are restricted to local energy conserving unitary. So by local energy conserving unitary, I mean those energy conserving unitaries that, let's say, couple system 1 to system 2 first, then you couple system 2 to system 3, and etc. So now from a classical intuition, you may expect that, well, energy can be redistributed in any arbitrary way just by a sequence of two local energy conserving operations. You bring energy from system 1 to system 2, and you can, by this local steps, we can redistribute the energy in any way we like. So, and this classical intuition suggests that there shouldn't be any restrictions, when we impose locality, basically, right? So this is basically the question we want to study in this talk. So, is this intuition correct or not? So here is the overview of the rest of my talk. I will first formally define exactly what I mean by these local symmetric quantum circuits. Then I present a kind of surprising result, the non-universality of local symmetric unitaries, the no-go theorem. And then I will explain how, in some cases we can circumvent this no-go theorem. And in particular, I talk about the application in the context of quantum thermodynamics. Again, this is just one particular type of applications, but I think this is perhaps more relevant for this conference. And finally, if there's time, I will talk briefly about overview of the proofs. Okay, so now let's try to define things more clearly. So this will be my running example, a system of n qubits with U1 symmetry. So for a system of n qubits with, I want to think about all rotations around Z, e to the I theta Z tensor n. So where theta is an arbitrary number between 0 and 2 pi, and Z is just Pauli Z. So this forms a U1 group. And I want to think about all unitaries that commute with this U1 group, or is invariant under the action of this U1 group, meaning that they satisfy this property for all theta. Equivalent to this property is equivalent to the conservation of some of the Pauli Z. So these are unitaries that preserve some of Pauli Z's. And depending on how you interpret this U1 symmetry, you have different interpretation of this family of unitaries. So for example, if you interpret this as spatial rotation around Z axis of a spin half system, then this will be just total angular momentum in Z direction. And these are unitaries that preserve angular momentum in Z direction. But you may also think about a different scenario where Z is the Hamiltonian of each qubit. And so then these are unitaries that preserve the total energy of these qubits. Now it can be easily seen that this family of unitaries, unitary V that satisfy this property, they form a group. And it's easy to characterize that group, at least in the case of U1. So let's think about a few examples. In the case of n equal to 1, a single qubit, this family of unitaries are just those that are diagonal in the 0, 1 basis, the eigenstates of Pauli Z. In the case of n equal to 2, so they are specified by just two parameters, phi 0 and phi 1. The phi 0 and phi 1 can be arbitrary phases. In the case of n equal to 2, I have three different sectors corresponding to three different Hamming weights, Hamming weight 0, Hamming weight 1, Hamming weight 2. And then in this sector, you can have arbitrary phase. In this sector, you can have arbitrary 2 by 2 unitary. And in this sector, you can have arbitrary phase again. And then finally, in the case of three qubits, I have four sectors corresponding to Hamming weight 0, 1, 2, and 3. And then in this sector, you can have arbitrary phase, arbitrary 3 by 3 unitary, again, arbitrary 3 by 3 unitary, and then arbitrary phase. Okay. So now I can define exactly, the simplest version of the question that I want to study. The simplest version can be asked just for a 3-qubit system. So for a 3-qubit system, meaning that for matrices, 8 by 8 matrices, I want to know if two local symmetric unitaries that are in this form, can generate all three, U1 invariant unitaries, all unitaries in this form. So can I just, for 3 qubits, just by coupling these pairs and then this pair and this pair, can I implement an arbitrary unitary in this form or not? So this is just the simplest version of the question. So I think this is a good point to pause. If there are any questions, please feel free to interrupt and ask. Okay, just I move on and just please feel free to stop me whenever there are questions. So I define, this is just the simplest version of the question. Of course, you can talk about also sets of unitaries that can be implemented by k-local symmetric unitaries. And note that in these definitions, I'm talking about k-local. When I talk about k-local, there's no notion of geometry, meaning that I can couple arbitrary far qubits to each other. But you can imagine that you also define a notion of geometry. For example, you can assume that all qubits are sitting on a 1D chain. And then you can imagine that we can add the constraint of geometric locality. So for example, not only the gates or the local unitary should act only on 2 qubits, it should act on 2 neighboring qubits, right? Just these neighbors. So this, you can impose these additional constraints, but it turns out that this doesn't change the set of unitaries that can be implemented by k-local unitaries, even if you require that the gates should act on neighboring qubits. Basically because, the swap unitary, the two local swap unitary that acts on 2 neighboring qubits, it can, change this. It's respect the symmetry for U1 symmetry or basically any other symmetry, it's respect the symmetry. And by composing these swaps on neighboring qubits, you can change the order of the qubits in any arbitrary way. And basically, this means that the particular geometry that you have chosen is irrelevant as long as they are connected to each other. As long as this graph that describes the neighboring qubits is a connected graph. Okay, so I define this problem in terms of quantum circuits, local unitaries. But equivalently, you can define exactly the same problem in terms of Hamiltonians. So think about all possible Hamiltonians that can be defined in the system and with these properties. The Hamiltonian can be written as sum of k local terms. Each term acts on k qubits. And the Hamiltonian comes with sum of zj's. So it has this U1 symmetry or preserved sum of zj's. Now the question is, what is the family of unitaries that can be generated under this Hamiltonian, under this family of Hamiltonians in Schrödinger equation? Okay, so it turns out that this family of unitaries that can be generated in this way is exactly, this set is equal exactly to the set of unitaries that can be implemented by k-local symmetric unitaries. And in a way, I mean, any circuit, so one direction is kind of obvious because any circuit, you can think of any circuit as a time-dependent Hamiltonian. So the fact that, this at the left-hand side is included in the right-hand side is kind of obvious, but you can also show that the right-hand side is also included in the left-hand side. Okay, so by studying the family of unitaries that are generated by k-local symmetric unitaries, I can also basically study this question. And this is an interesting question because characterizing that set is interesting because it basically allows me to think about constraints that are imposed on the time evolution of, possibly many body system that's whose Hamiltonian satisfy both locality and symmetry. So the question is, what are the consequences of locality and symmetry of the Hamiltonian and the long-term time evolution of the system? And does the symmetry of a local Hamiltonian have any additional implications beyond the standard conservation laws? So let's say, for example, if for this 1D chain, I know that the Hamiltonian has, let's say in this form, Hamiltonian is local and has a U1 symmetry. This is commutes with preserved sum of ZJs. So does the fact that it preserves sigma ZJs, it just tells me that there is a conservation law. So the question is, the fact that it's also local and preserves sum of ZJs, does it have any additional, does it put any additional constraints on the time evolution of the system or not? Okay, so with this, so far I've focused on the example of U1, but you can easily see that this is, this type of questions can be defined for arbitrary groups and arbitrary representation. Of course, in this talk, I'm just focusing on finite dimensional systems and finite dimensional representations. But you can think about, let's say, arbitrary finite or compact Lie group here, and you can imagine that the representation of group is different on different systems. So then we are interested in the family of unitaries that commute with the action of group, where the action is just this tensor product on all systems here. Okay, so all those questions now you can also ask them for general groups. Now here's the first main result. The first main result is non-universality of local symmetric unitaries. It turns out that in the case of continuous symmetries, such as group U1, a general symmetric unitary cannot be implemented using local symmetric unitaries. Okay. In fact, in the case of group U1 and this systems of qubit, it turns out that even k local symmetric unitaries for arbitrary k smaller than n, they cannot generate all k plus 1 local symmetric unitaries, right? So even if you have k, even k increases with the system size, but if as long as k is not equal to n, then there are some limitations, right? So it's very strong. Just going beyond 2 local doesn't solve our problem. Now you may imagine that you can't implement these unitaries exactly, but maybe you can get close to them. Maybe you can get arbitrarily close to the desired unitary using this k local or 2 local U1 invariant unitaries. But it turns out that that's not true. So we can show that the group of symmetric unitaries and its subgroup generated by k local symmetric unitaries are both compact connected Lie groups and hence closed manifolds. And so this is basically the schematic. This figure represents the schematic relation between the group of all symmetric unitaries and its subgroup generated by k local symmetric unitaries. So there are points, there are symmetric unitaries that you can't get arbitrarily close to them, and because these groups are basically compact. And it turns out that in the case of continuous symmetries, the dimension of the submanifold of unitaries generated by k local symmetric unitaries is generally less than the dimension of the manifold of symmetric unitaries. So yeah, this is basically, you are limited and you can't get arbitrarily close to those points. Okay, so let's go back to our running example of U1 symmetry. In this example, I have n qubits with U1 symmetry. And so the question is, what is the group? This is the subgroup generated by k local U1 invariant unitaries. And this is all U1 invariant unitaries. V and n is all U1 invariant unitaries. And the difference between the dimension, you can show that it's equal to n minus k. Okay? So as long as k is smaller than n, you don't have universality. This is the group of generated by k local U1 invariant unitaries. So in that simplest example that we discussed at the beginning, n equal to 3 qubits, group of all U1 invariant unitaries it turns out that it's 20 dimensional, and the subgroup generated by 2 local U1 invariant unitaries is 19 dimensional. So in particular, you can show that the family of unitaries, this family of unitaries generated by Hamiltonian Z tensor 3, They cannot be generated using two local U1 invariant unitaries, except a finite set of points in this family. For example, theta equal to 0 is identity, and obviously I can do it, but not generic values of theta. Okay. Now, so this was for general group, for U1 symmetry. For general groups, there's a bound. You can establish a bound like this. So I have to define some notations here. V and NG is the group of all symmetric unitaries, the group of unitaries that commutes with UG tensor N. So I am imagining that I have N subsystems or N QDIS perhaps. And so these are V's. So they all have the same dimension and the same representation of symmetry. And V commutes with UG tensor N. So, and VGNK is the subgroup generated by K local symmetric unitaries. So this is the subgroup generated by K local, and dimension. This is the dimension of. In other words, it's the number of real parameters that I need to specify a general group element. And so this bound says that the difference between the dimensions of all symmetric unitaries for a group G and the subgroup generated by K local symmetric unitaries is lower bounded by this quantity. What is this quantity? Irps of GK is the number of inequivalent irreducible representation of G that appears in UG tensor K. In other words, the number of inequivalent irreducible representation of G that appears on K subsystems. Okay? So this is irps of G, the number of irps that appear on N subsystems minus the irps of and number of irps that appear on K subsystems. Okay, so if we go back to our U1 example, just to understand how this bond works. So in the case of our U1 example, for K subsystems, for K qubits, the number of irps is just K plus 1, corresponding to K plus 1 Hamming weight that K bits can have from 0 to K. Okay, so this will be K plus 1. And so here my bound will be N plus 1 minus K plus 1, which is N minus K, which is the equal. And we know that in this case it holds as equality. Okay, are there any questions so far? Okay, so now in the case of continuous groups, I know that this quantity, irps of G, can grow unboundedly, right? So in the case of finite group, this has a maximum, which is just the size of the group G. But for continuous group, this can grow unboundedly, whereas this quantity is just determined by locality, and it remains locality of these interactions, and it remains constant. So as you see, the gap between the dimension of all symmetric unitaries and the dimension of the subgroup generated by K local symmetric unitaries grows unboundedly, basically. The gap, the difference between these two dimensions grows unboundedly. Okay, so it's kind of interesting, surprising, and maybe disappointing results for some applications. I will come back to this consequences of this result. But let's also think about the example of SU2 symmetry. So how this bound works for SU2 symmetry with, let's say, spin S system. So all subsystems are spin S, which means that they have dimension 2s plus 1. Then this bound becomes the difference between all SU2 invariant unitaries versus those that can be generated by K local SU2 invariant unitaries. It becomes this bound. This is the integer part of NS, where S is, takes this value is minus KS. Okay, again, it grows unboundedly with N. Okay, now, as I said, I mean, in some sense, this no-go results, can make us worried because, I mean, as I said, in some research theories, like research theory of thermodynamics, many results rely on the assumption that you can do arbitrary energy conserving unitary. So it's naturally we should try to find ways to circumvent this no-go theorem. And it turns out that in the case of U1 symmetry, we can circumvent it. We can show that in the case of group U1, this no-go theorem can be circumvented using an ancillary qubit. Just a single ancillary qubit is enough to circumvent this no-go theorem. An auxiliary system initially prepared in a fixed state that returns to the initial state at the end of the process. And can also show that using two local Hamiltonian xx plus yy and single qubit Pauli z, which are both invariant under rotations around z, it is possible to implement all unitaries which are invariant under this symmetry, provided that one can employ just a single ancillary qubit. Okay? So you can, for example, have a single ancillary qubit that interacts with every qubit on this chain via xx plus yy, you need to also apply Pauli z on this qubit. So these are Hamiltonians that you turn on and turn off. Or you can have this simpler geometry, 1D bit nearest neighbor interaction, provided that you allow ZZ interaction also. Okay, and now this was about U1 symmetry. U1 symmetry is closely related to energy conservation for systems with whose Hamiltonians are have equidistance energy gaps or energy levels, and so the no-go theorem implies that generic global energy conserving unitaries cannot be implemented using local energy conserving unitaries. But we can circumvent this using a single ancillary qubit again. So here's a theorem. Consider finite set of closed systems with the property that for each system, the gap between any consecutive pairs of energy levels is delta E. Then any global energy conserving unitary transformation in these systems can be implemented by a finite sequence of two local energy conserving unitaries, provided that one can use a single ancillary qubit or catalyst with energy gap delta E between these two levels. So the energy gap here should be equal to the energy gap here. And then by coupling this to this system by local unitaries, we can implement local energy conserving unitaries. We can implement an arbitrary energy conserving unitary. So how much time I have left?
You have about 4 minutes.
4 minutes. Okay. Okay, I can briefly talk about one of the ideas here. So first, let me explain. I mean, the main tool that I use for to study this problem is a Lie algebraic formulation of this problem, which is also used previously for proving the standard results on universality of two local gates. So in particular, if we have Hamiltonians plus minus A, for example, and plus minus B, and we can turn on and turn off them for arbitrary time, then by turning on and turning off them, we can implement Hamiltonian A plus B, and we can implement the commutator. And by repeating this, we can basically implement any Hamiltonian in the Lie algebra generated by A and B. And so this is the main this gives us a path to study this problem. So we studied the Lie algebra generated by local operators that satisfy symmetry. And so for example here, in this U1 symmetry problem, I have this two Hamiltonians which both have U1 symmetry, xx plus yy, and yx minus xy. They are two local and they have U1 symmetry. And then by coupling this, through, for example, a loop like this, I can generate, I can generate a Hamiltonian which is in this form: z2, z3, z4 minus z1. So this is now a three local Hamiltonian. So by combining these two local Hamiltonians, I obtain a three local Hamiltonians. But you can show that you can implement this kind of Hamiltonians, but for example, you can never implement ZZZ. You can just implement this type of Z, the Z acting on three qubits minus Z acting on three other qubits. So and then we can prove that this is impossible in general, and so I think I don't have enough time to just explain the rest. But the point is, by just thinking about this example and just preparing one of these qubits in a state zero, you can show that how you can implement now ZZZ, which is not a member of this Lie algebra, basically. Okay, let me skip this and go back to the summary. Okay, so summary, we started with this standard universality result, which basically implies that if the Hamiltonian is local, it can be written as sum of local terms, then there is no restriction on long-term time evolution of the system. And we know that, if the Hamiltonian is symmetry, then there are some standard conservation laws that are implied by Noether's theorem. Now, what this result tells us is that when you have both symmetry and locality, then there are some additional constraints in addition to standard conservation laws, basically. Okay, this is not an additive equation, basically. You get something extra. And here is, a more detailed summary of these results. So here is a preliminary version. I'm going to update this with some new results soon. Yeah, this is, as I said, this is still an ongoing project in my group. We are working on different aspects of this problem and its applications. I think it's a good time for me to stop, and I will be happy to answer your questions. Thank you.
Okay, great. Thanks, Iman, for a very interesting talk. And is there any questions or comments for Iman?
Hi, Iman. It's Yuji here. Hi, thank you very much for your nice talk. It's very interesting. I just wanted to check. I might have been missing something on the how to circumvent this no-go theorem using the catalyst uncertain state. So I thought you showed in the previous work that in the U1 case, the catalyst doesn't help in the sense that if you can transform by using a catalyst, then you can also do that without a catalyst. So how is that consistent with your result here?
So I guess you're talking about my work on resource theory of asymmetry.
Yes.
So yeah, this is a different scenario. In that scenario, you allow so there's no constraint of locality.
Mm-hmm.
You are assuming from the very beginning, you are assuming that you can do arbitrary, symmetric unitary, U1 invariant unitary, for example, right?
Mm-hmm.
And then you say, now what are the possible transformations under those U1 invariant unitaries, right? And then, the question is, what are the pure state to pure state transformation, for example, that are not possible without, that are not possible with symmetric unitaries and now become possible in the presence of catalysts. And there's that no-go result that you mentioned. But here it's a different scenario. Here we are talking about some restrictions that appear only because of locality and symmetry together, right?
Mm-hmm.
So these restrictions, now you can overcome these restrictions by a single ancillary qubit. And note that this single ancillary qubit is interesting, that it doesn't break the symmetry. You don't need a resource that breaks the symmetry. It's an eigenstate of Z, it's a state 0 or 1. Because at the end, you want to start with an operations that are symmetric, and you want to implement still an operation that
right.
You don't need a quantum reference frame, or you don't need a clock. It's just a I think the surprising thing is that a single ancillary qubit is enough.
I see.
That's kind of that was kind of surprising to me. And first I showed that it's just 2 ancillary qubits, and then I realized even a single ancillary qubit is enough.
I see. So intuitively, this ancillary qubit helps to globalize the transformation in a sense.
Yes. Yeah. Exactly.
Right.
There are different ways to interpret this. I'm going to add some of these interpretations in this next version of the paper that will be posted. So.
Okay. Very nice. Thanks.
Sure. No problem. Thank you.
Okay. Due to the time limits, so maybe let's move more discussion to Slack channel, and let's thank Iman again.